Hi everyone, my name is Edmond Cheung and I'm a newly minted doctor from UC Santa Cruz, about to start my postdoc at the IPMU in Japan come October. Today I'll be discussing my recently submitted work which asks the question, can bars fuel AGN? And this work is in collaboration with several people, including several who are in the room today, including Dale, Eric, Sandy, David, and Jerome. So, can bars fuel AGN? Well, the first question to ask is, how would bars fuel AGN? And this process consists of two steps. Step one, get the fuel drunk at a bar. And in this case, it's an unsuspecting astronaut, and he is indeed drunk at the space bar. Step two would be to throw the drunken astronaut into a black hole, and that's how a bar can fuel an AGN. But in all seriousness, a bar can fuel an AGN by funneling gas into the centers of their host galaxies. And this process has been shown by many works, including those of, including Leah Athnasula's 1992 works, which models the behavior of gas under bar potential in isolated disk simulations. These two top panels up there are from that work. The upper left is gas density and the upper right is the gas velocity field. And what I want you to see is that for the densest locations of the gas densities, if I had a pointer I would show you, it mirrors the locations of where the gas velocity discontinuities are, i.e. where the shocks are. And this is mirrored, here's a little laser. Okay, so right here are where the densest gas densities are, which is mirrored in the locations of the gas velocity discontinuities, i.e. where the shocks are. And this is mirrored in the actual locations of barred galaxies, the dust lanes in barred galaxies. So simulations and observations argue that gas gets shocked along the bar ridge lines where it loses energy and falls in towards the center of the barred galaxy, and which can thereby potentially lead to the fueling of an AGN. But do bars really fuel AGN? I'll answer that question in a minute, but let's first review the current literature on the subject about what fuels AGN. And for the most luminous AGN, it seems that major mergers are the main triggers. And here's a plot of fraction of AGN versus AGN luminosity by Tracer et al. 2012. And it seems for the most luminous AGN, most of them are indeed in major mergers, indicating that major mergers do fuel the most luminous AGN. But for low to intermediate luminosity AGN, this doesn't seem to be the case. Dale showed earlier in his 2012 work, for a sample of Z2 galaxies and candles, using a variety of merger signatures, disturbed 1, 2, 3, and close companions. The intermediate luminosity AGN, shown by the red triangle, are no more likely to be in mergers than the control sample of inactive galaxies, shown by the blue squares. So, if not major mergers, then what fuels these moderate luminosity AGNs? Well, Dale's study also showed that the majority of these moderate luminosity AGNs are hosted by galaxies with substantial disk structures, suggesting that whatever triggers these moderate luminosity AGNs cannot destroy the disky structure of the host. So an obvious process that satisfies this constraint is bar-driven secular evolution. So is there any past evidence that bars can fuel AGN? Well, Mulcahy and Regg in 1997 addressed this question by asking a related question. Is there an excess of bars among AGN hosts? If there is, then it means that nuclear activity or the presence of a bar is correlated with nuclear activity, indicating that bars do indeed fuel AGN. But they found for their sample of AGNs, in this case Seifert's, its bar fraction is no different than the bar fraction of its control sample, indicating that there is no excess of bars among AGN hosts. And this result has been confirmed by many works since, and here's a short list of them that just scrolled by. But a limitation of all previous works has been that they are all limited to Z of 0, where the number density of AGNs is at its lowest. And here's a plot of the number density of AGN versus redshift. And at Z of 0, you can see the number density is indeed at its lowest. So that's where our work comes in, and we ask, for the first time, is there an excess of bars in the AGN hosts beyond the local universe, where you can see that the number density of AGNs is substantially higher than that at Z of 0. If there is a bar-AGN connection, then this represents our best shot at capturing it. So in order to conduct this experiment, we first need to find a sample of AGNs. And we aim to find moderate luminosity AGNs defined by this luminosity range. So we use archival Chandra data in the Aegis, Cosmos, and Good South survey And we want obscured AGN, so the AGN light doesn't dominate over the host. And we restrict this to a redshift range of 0.2 to 1.0. Beyond 1.0, redshift of 1.0, redshift effects dominate, and it's really hard to identify bars in an accurate manner. So with our AGN sample, we then want to control it to a sample. We want to compare it to a sample of non-AGN galaxies matched to this AGN sample in 5 parameters. And these 5 parameters are stellar mass, red frame color, Sirsic index, half-light radius, and redshift. And we chose these 5 parameters because they've been shown to correlate with both the presence of a bar and the presence of an AGN. So in order to uncover any underlying bar-AGN connection, we need to control for these 5 parameters. Now what follows is an illustration of our matching technique. So shown here is an actual AGN galaxy from the Aegis survey. And our goal is to find 3 unique non-AGN galaxies matched to this AGN galaxy. So the first step is to find all non-AGN galaxies that is within 2 to 3 times this AGN stellar mass, red frame color, Sirsic index, half-light radius, and redshift. And here they are. Now with this initial pool of control galaxies, we then iteratively reduce it until we find the 3 best matched control galaxies, which I show now. So with this initial pool, we then reduce it to the 15 control galaxies that are best matched to this AGN's redshift. And there they are. Then we find the 12 control galaxies out of these 15 that are best matched to this AGN's red frame color. And there they are. Now we find the 9 best matched this AGN Sirsic index, 6 best matched this AGN's half-light radius, and finally the 3 control galaxies that are best matched this AGN stellar mass. And this is an example set of an AGN and its 3 control galaxies. We do this matching technique for every AGN in our sample. So how well does our matching technique work? Well, we can assess this by looking at the differences in the matching parameters of the AGNs and the controls. So for example, we can take a look at the difference in the stellar mass between the AGNs and the controls and look at their distribution. And here it is. So you can see that the distribution of the stellar mass differences are centered around 0 with a small dispersion, indicating that the stellar masses of the AGNs and the controls are pretty well matched. But you may have noticed that the matching technique that we employ depends on the order in which we match the AGNs to the controls and the order in which we use the matching parameter. So in order to adequately sample the parameter space, we repeat this matching technique many times, with each iteration shuffling the order of the AGNs, the order of the controls, and the order of the matching parameters. So make another matching iteration, we'll come up with another control sample, and we can take a look at, again, the difference in the stellar masses between the AGNs and the controls. So I overplot that histogram over the previous one. You see that it looks pretty similar. We can do another matching iteration, get another control sample, and then we can take another difference in the stellar masses again. And overplot that histogram. We do another matching iteration, overplot it over there. Ultimately, we repeat this matching technique 100 times, resulting in 100 control samples. And we have 100 histograms, which I stack together right there. You can see that the most occupied parameter space is around 0 with a small dispersion, indicating that the stellar masses of the AGNs and the controls are pretty well matched. Now, here are the matching parameters for all 5 matching parameters: red frame color, half-light radius, Sirsic index, and redshift. And they're all peaked around 0 with a small dispersion, indicating that the AGNs and the controls are well matched in these 5 parameters that we chose to match upon. Here are 2 example sets of an AGN and their 3 control galaxies. Here's an AGN, 3 control galaxies, AGN host, 3 control galaxies. And what I want you to see is that they look similar in appearance, indicating that our matching technique works reasonably well. Now, with this AGN sample and the control sample, we now use the Galaxy Zoo Hubble bar classification to ask the question, is there an excess of bars among AGN hosts beyond the local universe? And here are the results. So plotted here is the bar fraction of the AGN in the green square and the bar fraction of all 100 control samples in the small gray triangles. The large purple triangle represents the median bar fraction of all 100 control samples. And what you can see is that the bar fractions of the AGN sample and the control samples are not very different at all. There is no statistically significant enhancement of the bar fraction among AGN hosts. And this result is found for all 3 surveys we considered. The Aegis survey, which was what we just looked at, Cosmos in the center, and then Good South on the right. there is no statistically significant enhancement of bars, of the bar fraction among AGN hosts across all 3 surveys, indicating that bars are not the primary fueling mechanism for the growth of supermassive black holes in this redshift range of 0.2 to 1.0. Combining our result with those in the local universe indicates that we can stretch this down even further. Bars are not the primary fueling mechanism for the growth of supermassive black holes since Z of 1. And this epoch corresponds to a time in which 50% of the local black hole mass density has been built. Here's a plot from Aird et al. 2010, and it shows the black hole mass density versus look-back time. And at Z of 1, which is shown here, 50% of the local black hole mass density has been built, meaning that bars are not responsible for the buildup of at least half of the local black hole mass density. And finally, because the AGN number density peaks at Z greater than 1, and because the bar fraction plunges at Z greater than 1, it's likely that bars have probably never been the dominant fueling mechanism for the growth of supermassive black holes. So you may ask, if not bars, then what? What fuels AGN? Well, it may be just, there may not be a large-scale process that results in the fueling of AGN. Instead, it could be a collection of processes that somehow wind up together and feed an AGN. For example, maybe minor mergers, cooling flows, or multi-body interactions with nearby star clusters or other clouds. And collectively, this process has been grouped together under the name stochastic fueling, and there's been a recent paper by Phil and Dale, which I refer you to if you want to hear more. But let me end with the main result of our work, and that's large-scale bars are not the primary fueling mechanism for the growth of supermassive black holes over cosmic time. Thank you.
Questions?
I think they're convinced.
I'm a little confused about the definition of a bulge in the bar. You know, if you have supermassive black hole, really massive, you need a bulge.
Sure.
Otherwise, it can't be supermassive. So, how much bar can you then still have? You know, I mean, if you have a 10 to the, let's say 10 solar mass bulge or something more, is that part of the bar, or is it
No, because the typical half-light radii of stellar bulges are about 1 kiloparsec, and the typical scale radius, semi-major axis of a large-scale bar is about 3 kiloparsecs, and that's beyond the 1 kiloparsec.
Sure, but then the bulge would prevent the gas from really spiraling to the center, because the bulge is a more spherical potential, and the bar might fuel the gas into the bulge, but then it gets stuck, so no wonder that in some sense it's obvious.
So you're saying you don't disagree with this, but you thought it was a dominant?
No, I think it's kind of trivial in some sense.
Well, okay, the typical idea was that it was the bars within bar scenario. So I skipped that. So yeah, once you have a large-scale bar that funnels gas within 1 kiloparsec, you need another bar, inner bar, within 1 kiloparsec to funnel the gas into 10 parsecs. So to really fuel an AGN with bars, you need 2. And according to local studies,
did you really then check the inner bars?
well, we can't resolve the inner bars in these Hubble images.
That's not really done the right question, you know?
Well, okay.
Then you should have looked for this.
Sure, but we can't do that right now. But if we
Bring your telescope in space.
But then the question is still open whether.
well, if you take the results from the local universe, they show that inner bars don't correlate with AGN activity either, and they show that large-scale bars didn't either. So there's a lot of evidence in the local universe that indicates that bars, no matter what size, just don't fuel an AGN, and this work is it's consistent with that so far. But the inner bars, I grant you, we haven't explored that at all. Locally, spiral galaxies do have bars, yes. 60% if you ask. 66%. Well, 66%, but yes. Well, you'd expect if a bar did fuel an AGN, you'd have nuclear activity in more bar hosts than none. Maybe, perhaps. But that was the question that we were asking, and we didn't find that.
Well, if the incidence is equal, then it doesn't matter, right? I mean, it's No, I mean, if the incidence is equal, then it's saying that AGN activity does not care about whether there's a bar or not. So yes, half of gal galaxies could be barred, but if there's no extra. I had one question. So there was, so one of the limitations of this, you restricted your range in X-ray luminosity to make sure that you avoided the brightest point sources in the middle.
Right.
To which extent do you think that would make a difference if one went to, if one started masking the point source or the point in the middle and redoing the classifications, etc.? Could you go to higher luminosities? Do you think that that might make a difference?
I think for the highest luminosity AGNs, the major mergers are probably the main triggers. And if we mask a high bright point source, like these high luminosity AGNs, perhaps we could see something, but I'm in the mindset that that's been sort of handled by major mergers.
Any other questions?
That's a quick question, but
Oh, go ahead.
time scales, time delays in these inner bars. So obviously, if there's a time delay between the bar sends gas down and AGN triggers, it might actually wash out the connection. That's the norm. Then, do you know if locally it's known what the time delay is between outer and inner bar, the observance of the inner bar? So the question is whether the inner bars are actually doing heating. Because if there is a time delay, then perhaps that's why it's getting washed out. If there's no time delay, then you know the inner bar should be present.
Well, let me address that by saying that there's no correlations with large-scale bars and nuclear bars. So that's one way that you would think if you feel an AGN with bars, you kind of need both of them. And since there's no correlation, that kind of messes things up.
And bars typically live for a long time.
According to who you asked, but according to Leah Ethnosula, it lasts for about 10 gig years. According to other people, maybe 2 gig years. But yeah.
But it's still a heck of a lot longer than AGN.
Absolutely.
Yeah, so it shouldn't be, the bar shouldn't be disappearing and then the AGN turning on. If you didn't know it was there.
Cool. Thank you, Edmond.